Welcome back to the A+ Tutor. Today we're going over exponential growth and decay and their applications. Exponential growth or decay is when a value changes rapidly. Specifically, this happens when a quantity increases or decreases by the same factor over equal intervals of time. So if we look at a couple graphs, exponential growth will look something like this, but exponential decay will kind of be the opposite and look like this, because exponential growth is going to grow really, really fast or exponentially, and exponential decay is going to fall really fast or decrease exponentially. There are two ways to consider exponential growth and decay. First, you have quantities that grow or decay by a fixed percentage at regular intervals, and then you have quantities that grow or decay continuously. So a quantity that might grow or decay by a fixed percentage at regular intervals are something that maybe doubles every hour. We know every single hour, which is our regular interval, we're going to double our value, which is our fixed percentage. Something that grows or decays continuously may be something like population. We know that every 10 years, we grow at a rate of 5%, but that's constantly growing. So for our fixed growth or continuous growth, we have a few different formulas that we use. Firstly, our general form of the exponential equation is f of x equals ab to the x power. So when we're looking at our growth and decay functions, our growth and decay for fixed exponential growth is going to be f of x equals a times 1 plus or minus r raised to the power of t. A is our initial value, r is our rate of growth, and then t is time. So whenever we are growing by a fixed percentage at regular intervals, we will use this formula to determine what that exponential growth or decay is. Now, on the flip side, when we have our continuous growth or decay, we use a different formula and we actually use E, or Euler's number, to represent this continuous growth or decay. So whenever we have continuous growth, our formula is P equals P0 E raised to the RT power or to the negative RT power if it's decay, where P0 is our initial quantity, R is our constant rate of growth, and then T is still time. Let's look at an example of each of these. So let's start with exponential growth, considering bacteria growth. Consider a bacteria that doubles every hour. How many bacteria will be present after 8 hours? Let's do a little graph just to visualize what this looks like. So we know over time, we're going from 0 hours to 8 hours, and 0 is where we're starting. We're going to be doubling our bacteria. If we start with 1 bacteria, then after 1 hour, it doubles and we'll have 2. The next hour, it's going to double again and we'll have 4. The next hour, it doubles again and we have 8, and so on until we get to 8 hours and we'll have 256 bacteria present. So to answer this, we have our answer, it's 256. But how could we find this faster without having to create this table? Or how can we figure out how much bacteria is present after 100 hours, after 1,000 hours, after whatever amount of time that we want to find? This is where our formula becomes really helpful. So if we look at our table, we know that that initial value is 1. That's our starting point. And then if we look at this pattern, we have 1, then we have 2, then we have 2 times 2, which is 4, then we have 2 times 2 times 2. So we're constantly taking the previous value and multiplying it by 2, or we have 2 raised to a certain power. So in the very beginning where we have our initial value, we have 2 raised to the 0 power, which is our time, and that's 1. 2 raised to the first power, our time is 1, and that's 2, and so on and so forth. So we can see that we can represent this using an exponent just by noticing what this pattern is. Let's look at what this graph looks like. When we graph this, we see the same thing we saw earlier with how exponential growth is modeled, and we see that this grows exponentially or very rapidly once we get to hour 6, 7, and 8. We go from being kind of flat and on the same line, but then we all of a sudden shoot up to over 200 bacteria present. And that's how you can see that there is exponential growth. So let's take our formula, which is y equals a times 1 plus r raised to the t power. Our a is 1 because that's our starting or initial value. Our rate is 100% because after every hour, we're increasing by 100% of what we had before. So our rate is 100% or 1. So if we plug all of that in, we get y equals 1 times 1 plus 1 raised to the t power, or y equals 2 to the t power, which is exactly what we found when we saw our pattern earlier. Now let's look at an example for exponential decay, and this time let's look at a tournament bracket. So a tournament starts with 64 teams, and after each round, half of the teams are eliminated. So how many teams are left at round 5? Again, we can visualize this by making a table with the number of rounds on top and the number of teams remaining on the bottom. In our initial round, or round 0, we start with 64 teams. After the first round, half of the teams are eliminated. So now we have 32 teams, 64 divided by 2. In the next round, half the teams are eliminated and we have 16. Round 3, we have 8. Round 4, we have 4 teams left. Round 5, 2. And in the last round, which is round 6, we're left with 1 team, which would be the winner in this case. So again, we want to notice what pattern we have. And here, we're multiplying each of these values by 1/2 every time. So we start with 64. We multiply that by 1/2 to get 32. Multiply that by 1/2 to get 16, or 64 times 1/4 gives us 16. 64 times 1/8 gives us 8, and so on. So we can see that we are really multiplying by 1/2 raised to some power for each round. And if we graph that, we'll see that decay. We see the huge drop from round 0 to round 1, and then another large drop from round 1 to round 2, and then it starts to kind of flatten out until the graph ends at round 6. So we absolutely do not have continuous growth here because we cannot keep having rounds of this tournament with 1 team left. So the way that we'll look at this in our expression is we'll use our exponential growth and decay formula, which is y equals a times 1. Since we have decay, this time it's going to be minus r raised to the t power. Our a, or our initial value, is 64, and our rate is 50% because we're losing 50% each time, which is equal to 1/2. Plugging those in gives us y equals 64 times 1 minus 1/2 raised to the t power, which is 64 times 1/2 raised to the t power, or we can write this as 64 over 2 to the t power. Both are correct. But this gives us our exponential decay over time, which is the number, which is our rounds, and we're able to represent this using this formula. So if we had 1,000 teams over 10 rounds, we could figure out how many teams are left after 4 rounds by using this formula. We would replace our initial value and then replace our t, and we would be able to solve that. So those were 2 examples with constant rate over regular intervals. Now let's look at a continuous exponential growth or decay using a half-life example. So a hospital prepares a 100 milligram supply of technetium-99, which has a half-life of 6 hours. We need to find the decay factor, write an equation to represent this scenario, and find the amount of technetium-99 that remains after 75 hours. So first, let's find the decay factor. We're going to do this by using our second equation, P equals P0e to the RT. And we know that after 6 hours, we have half of our initial sample. So P at 6 is equal to 1/2 of P0. If we plug these things in and set these equal to each other, we're able to solve for our rate. So 1/2 P0 equals P0e to the 6r, because our time is 6. Our P0s cancel, and we're left with 1/2 equals e raised to the 6r power. To get rid of our e, we need to do the opposite. So we take the natural log, or ln, on both sides. On the left side, we'll have ln 1/2. On the right side, we'll have 6r. So r, solving for r, gives us ln 1/2 divided by 6. And if we plug this into our calculator, we are left with negative 0.116 or 12%. So our decay factor, this technetium-99 decays at a rate of 12%. So now we can use this to write an equation to represent the half-life. So P of T is equal to our initial value, which is 100, times e raised to the negative 0.12 T power. Now, to find the amount of technetium-99 that remains after 75 hours, we're going to plug in 75 for T. So P of 75 is equal to 100 times e raised to the negative 0.12 times 75 power. Plugging that into our calculator gives us approximately 0.017 milligrams remaining of technetium-99. Now let's use these formulas to solve real-world examples. The world's population in 2000 was approximately 6.08 billion. The annual rate of increase was about 1.26%. We need to find the growth factor for the world's population. Suppose the rate of increase continues to be 1.26%, write a function to model the world population, and let x be the number of years past 2000, find the world population in 2010. So for this example, we're going to use our regular exponential growth function, which is f of t equals a times 1 plus or minus r raised to the t power. That 1 plus or minus r is our growth factor. So when they ask us to find the growth factor, we're looking for 1 plus or minus the rate. In this case, since we are increasing in population, we're going to do plus as our operator. And if our rate is 1.26%, let's convert that to a decimal number. So divide by 100 and we get 0.0126. So our growth factor is 1 plus 0.0126 or 1.0126. That means our function to model this growth is f of t equals 6.08 times 1.0126 raised to the t power. If x is the number of years past 2000, we need to find the world population in 2010. So if we're in 2010, x would be equal to 10 because 2010 minus 2000 is equal to 10 years. We plug that in for our t, so y equals 6.08 times 1.0126 raised to the 10th power. Plugging that into our calculator gives us 6.89 billion. So in 2010, our world population is 6.89 billion. Now you may ask why we didn't use our other formula for population. In this case, we could have, and we would get the same value because this is a continuous growth. So we would see that we would get the exact same value for our population in 2010. Phosphorus 32 is used to study a plant's use of fertilizer. It has a half-life of 14.3 days. Write the exponential decay function for a 50 milligram sample and find the amount of phosphorus 32 remaining after 84 days. So for this one, we're going to use our continuous exponential growth or decay function because we're dealing with half-life. So that equation is P of t equals P0 e raised to the RT power. For our half-life, our t is 14.3 days. So P at 14.3 days is equal to half of our initial quantity, or 1/2 of P0. So 1/2 of P0 is equal to P0 times e raised to the 14.3 times r power. Our P0s cancel and we're left with 1/2 equals e raised to the 14.3 r power. Take the ln of both sides in order to get rid of our e. So ln of 1/2 is equal to 14.3 times r. Divide both sides by 14.3, and r is about negative 0.048 or negative 4.8%. So our rate of decay is 4.8%. This means our exponential decay function is P of t equals, our initial value is 50. So 50 times e to the negative 0.048 t power. Now we need to find the amount of phosphorus 32 remaining after 84 days. So we'll plug in 84 for t, and P of 84 is equal to 50 times e to the negative 0.048 times 84 power. And this is equal to 0.85 milligrams. So we have 0.85 milligrams remaining after 84 days. A computer valued at $6,500 depreciates at the rate of 14.3% per year. Write a function that models the value of the computer and find the value of the computer after 3 years. So we know that our initial value is $6,500 and our rate is 14.3%. And we already know that this is decay because we're told that the value depreciates each year. So this means that we're going to use our equation f of t equals a times 1 minus r raised to the t power. So this means our function that models this is going to be f of t equals 6,500 times 1 minus 0.143 raised to the t power, or 6,500 times 0.857 raised to the t power. Now we need to find the value of the computer after 3 years. So we're going to plug in 3 for t. And we get f of 3 is equal to 6,500 times 0.857 raised to the third power. And this is equal to $4,091.25. So after 3 years, this computer is now worth just over $4,000. For a period of time, an island's population grows at a rate proportional to its population. If the growth rate is 3.8% per year, and the current population is 1,543, what will the population be 5.2 years from now? So we're going to use our continuous growth formula, P of t equals P0e to the RT. Our R is 3.8%, or 0.038, and our initial value, or P0, is equal to 1,543. So we know that our growth expression is P of t equals 1,543 times e raised to the 0.038 t power. If we plug in 5.2, we're going to get P of 5.2 equals 1,543 times e raised to the 0.038 times 5.2 power. And plugging this into our calculator gives us approximately 1,880 people in 5.2 years. A new truck that sells for $29,000 depreciates 12% each year. Write a function that models the value of the truck. Find the value of the truck after year 7. So again, they're telling us that it depreciates, so we know that we have exponential decay. Our initial value is $29,000 and our rate of decay is 12%. So we're going to use the formula f of t equals a times 1 minus r raised to the t power, where our a is 29,000 and our r is 12%, or 0.12. Our function that models the value of the truck is going to be f of t equals 29,000 times 1 minus 0.12 raised to the t power, or f of t equals 29,000 times 0.88 raised to the t power. Now let's plug in 7 for t. So to find the value of the truck on year 7, we will do f of 7 equals 29,000 times 0.88 raised to the 7th power, which is equal to $11,851.59. Radioactive isotope carbon-14 decays at a rate proportional to the amount present. If the decay rate is 12.10% per 1,000 years, and the current mass is 135.2 milligrams, what will the mass be 2.2 thousand years from now? So we're going to use our continuous growth formula. That is P of t equals P0e to the RT. And we will use this to figure out our mass in 2.2 thousand years. So our rate is 12.1%, or 0.121, and our initial value is, or the current value is 135.2 milligrams. Our t is going to be 2.2 years. We can plug these things into our formula, and we know that it's exponential decay, so we need to do negative r and not positive r. So P of t is going to be equal to our initial value, 135.2, times e raised to the negative 1.21 t. Plugging in 2.2 to solve for the mass in 2.2 thousand years, we'll get P of 2.2 equals 135.2 times E raised to the negative 0.121 times 2.2 power, and that's equal to approximately 103.6 milligrams of carbon-14. An investment of $75,000 increases at the rate of 12.5% per year. Find the value of the investment after 30 years. We're going to use our regular exponential growth formula for this. This isn't anything like compound interest. We're just being told the investment increases 12.5% per year. So after 30 years, what will this be worth? So we're going to use f of t equals a times 1 plus r raised to the t power. Our a in this case is 75,000, and our rate, or r, is 12.5%, which is 0.125. This gives us a formula of f of t equals 75,000 times 1 plus 0.125t, or 75,000 times 1.125 raised to the t power. When t is equal to 30, we'll plug that in for our t, so we'll get 75,000 times 1.125 raised to the 30th power. This is going to be equal to $2,568,247.87 in 30 years. A savings account balance is compounded continuously. If the interest rate is 3.1% per year and the current balance is $1,077, in how many years will the balance reach $1,486.73? So now we are dealing with compound interest, and we're compounding this continuously. So we need to use our other exponential growth formula. That is going to be P of t equals P0 e to the RT. When we are talking about compound interest, you may also see this formula written in the way A equals PE to the RT power, which is the exact same thing. The only difference is instead of A, we have P, and instead of P, we have P0. So it's the exact same formula. Our rate is 3.1%, which is 0.031, and our initial value is 1,077. What we want to find this time is t when our P of t is equal to $1,486.73. So we're going to set 1,486.73 equal to 1,077 e raised to the 0.031 t power. We'll divide both sides by 1,077, which gives us 1.38 equals e raised to the 0.31 t power. Let's take the ln of both sides, the natural log, in order to get rid of our e. So 0.322 is equal to 0.031 t. Divide both sides by that rate, which is 0.031, and we'll get t is equal to 10.4 years. So it'll take 10.4 years to reach $1,486.73. The population of an endangered bird is decreasing at a rate of 0.75% per year. There are currently about 200,000 of these birds. Write a function that models the bird population. How many birds will there be in 100 years? Our rate is 0.75%, which is 0.0075, and our initial value is 200,000. We're going to use our regular exponential decay function for this. So f of t equals a times 1 minus r raised to the t power. So that means our function that will model this decay, or this rate of decrease, is going to be f of t equals 200,000 times 1 minus 0.0075 raised to the t power, or 200,000 times 0.9925 raised to the t power. If we plug in 100 for t, we're going to get 200,000 times 0.9925 raised to the 100 power, which is approximately 94,206 birds remaining. During the exponential phase, E. coli bacteria in a culture increases in number at a rate proportional to the current population. If the growth rate is 1.9% per minute and the current population is 172 million, what will be the population 7.2 minutes from now? So we'll use our second exponential growth function, P of t equals P0 e to the RT. Our R is 1.9% or 0.019, and our P0 or our initial value is 172 million. So our expression to represent this growth is going to be P of t equals 172 times e raised to the 0.019 t power. Now we want to find this value in 7.2 minutes, so we're going to plug in 7.2 for t, and P of 7.2 is equal to 172 times e raised to the 0.019 times 7.2 power. Plugging that into our calculator gives us 197.2 million bacteria. The bear population increases at a rate of 2% per year. There are 1,573 bears this year. Write a function that models the bear population. How many bears will there be in 10 years? So we'll use f of t equals a times 1 plus r raised to the t power to represent this. Our rate is 2% or 0.02, and our a, or our initial value, is going to be 1,573. So the function that represents the bear population will be f of t equals 1,573 times 1 plus 0.02 raised to the t power, or 1,573 times 1.02 raised to the t power. Now we'll plug in 10 to find out how many bears there will be in 10 years. So f of 10 is equal to 1,573 times 1.02 raised to the 10th power, which is about 1,917 bears in 10 years. SR85 is used in bone scans. It has a half-life of 64.9 days. Write the exponential decay function for an 8 milligram sample. Find the amount remaining after 100 days. We'll use our exponential decay function, P of t equals P0e to the negative RT, because it's exponential decay. And we need to find our rate of decay. We know the half-life is after 64.9 days. We can find our rate using the half-life. 1/2 of P0 is equal to P0e to the R times 64.9. Our P0's cancel, so 1/2 equals e raised to the R times 64.9 power. Take the ln of both sides, and we get ln of 1/2 is equal to 64.9 R. Divide both sides by 64.9. Our rate is negative 0.0107, or about 1%. So we can represent this exponential decay with the formula P of t equals 8, which is our initial value, times e to the negative 0.011 t power. Now to find the amount remaining after 100 days, we'll plug in 100 for t. So P of 100 equals 8 times e to the negative 0.011 times 100, which means there is 2.75 milligrams remaining after 100 days. Thank you so much for watching. I hope you enjoyed. Don't forget to like and subscribe, and check out my channel for more videos. If there are any topics you'd like for me to go over, leave a comment down below. See you next time.